Time for another video. Nice. We're getting to the end of Chapter 5, so this might actually be one of the last ones. Section 5.6 is similar to 5.5, because 5.5 dealt with inequalities within one triangle, the way we could compare some of the side lengths to each other, and the way we can compare some of the angle measures to each other inside of one triangle. Section 5.6 is called something like two triangle inequalities, because now I'm going to be comparing sides and angle measures in different triangles between one to another. So one of the ways that we're going to do this is something called hinge theorem. So feel free to, you know what, if you're actually looking at this video on a computer, you could look at this GSP file, 5.6 hinge theorem GSP, while you're watching the video at the same time. So I recommend that. Why not? So for now, instead of me just actually telling you the theorem, let me kind of just line up so we can see what it's going to be telling us, really. I got two triangles, ABC and DEF. Makes sense, I guess. And it appears that right now they're congruent, because we're told angle B and angle F are 90 degrees, so we have SAS congruence, so these two things are congruent. Cool. But what if I were to move point C such that they weren't congruent? What if the red lengths are fixed and the green lengths are fixed, so that no matter what we have two congruent sides, but I were to change either angle B or F so that we don't have SAS anymore. We change one of the A's to be different than the others. So like, for example, I'll pull C in. If I pull C closer to A, then angle B becomes no longer right, but acute. That's this guy. And what does that do to the orange side length here, the third side length? The way it compares to the green one now, well, I guess CA is 13.89 as opposed to ED being 17.49, so now it's less than it. So hinge theorem is called that because it kind of looks like you're opening and closing a door where this angle is the hinge of the door, and it lets us compare this orange dotted line to this blue dotted line, line segment, if I'm being precise, actually. So it looks like as angle B decreases, the side length AC gets shorter than this blue dotted one DE. However, if I pull C further away, if I widen this hinge, then I have side length CA measuring about 20, whereas ED measures about 17.5. So it sure does look like if they're the same angle, if I have SAS essentially, if this angle, which is called the included angle between the two sides, if the included angles are the same between two triangles, then they are congruent because of SAS. If one is less than the other, then its opposite side is going to be less than the other triangle's opposite side. And if angle B is, or the included angle is greater than the other triangle's included angle, then its opposite side is going to be greater than the second triangle's opposite side. How about that? So in words, oh my gosh, a whole bunch of words, what this is essentially saying, what hinge theorem is essentially saying, is pretty much what I just specified. If I have SAS minus the A, the difference in the A tells us which of the opposite sides is greater than the other. So take a second to soak this in before I actually pop into the normal notes and give some examples, some concrete examples. On the top of this page, what I've done is my best to kind of condense hinge theorem into a nice, digestible one-sentence phrase. If you need to, go ahead and pause the video and take a look at that, but what I essentially have underneath is the non-GSP version of what I was trying to do, which is that I have two pairs of congruent side lengths, the 1 marks and the 2 marks between a couple triangles, as I start expanding this angle. It goes from 50 to 90 to 115. Well, that's going to do something to the side opposite it, the one that's dashed. So what that's essentially going to do is it's going to make it larger, because the two vertices are getting further apart, the wider the angle opposite the that dashed side gets. By the way, gnome there. Gnome. So what we could say is, like we did last section, if we want to compare the measures from the sides, we could do so with an inequality. So here I could say that because I have hinge theorem here, the two pairs of sides between all these three triangles, 50 is less than 90, which is less than 115, so that tells me A is going to be less than B, which is going to be less than C. So I could use the converse to this theorem too, which does exist. It is a thing, and it is true. The converse is true in this case, so it's biconditional. Which would essentially say the same thing if I was given, if I wasn't given the angle measures. Pretend I wasn't. Pretend I wasn't given those. Let's call them D, E, F. So if I have that, and I have that this is, I don't know, 15, and this is 20, and this guy here is 25, well, I could set up a similar inequality with the angles here, according to the converse to the hinge theorem. I could say D is less than E is less than F, because the sides opposite them will increase in the same order. Sure. And also, if you're wondering, like, oh, geez, do I have to know hinge theorem? Do I have to, like, memorize it for a proof table? Do I have to know what's the difference between it and its converse? Nah, don't worry about that. You only have to know how to use these things for computations, not actually proving anything. Don't worry. Speaking of knowing these things for the sakes of computations, let's work with quadrilateral soup here. See? Soup. Soup. So what I can do is I can apply hinge theorem in this case. And again, I mean, I guess it was obvious that I was going to apply hinge theorem because it's the only thing we've learned so far in this video. But I recommend you pausing this, you taking a look at these, and you're trying it yourself. So, pause, and I'm going... Now, hinge theorem. Okay, so hinge theorem relies on two pairs of congruent sides, which we seem to have between these two triangles. There's SU being reflexive to itself. There's SO being congruent to PU, because they both measure 30 centimeters. And then if I want to compare angle OSU, hang on a minute, if I want to compare angles OSU to SUP, I could do that by applying hinge theorem. So OSU is the blue one, SUP is the double green arced one. And what I could say is, alright, so 23 is smaller than 24. So I guess the angle that's opposite 23, so angle OSU, measure of angle OSU, that's going to be less than the measure of angle SUP. Strictly because of hinge theorem, because the side opposite the blue arc was less than the side opposite the double green arc. That one's actually the converse to the hinge theorem, but yeah, don't get bogged down by which one's the real one and which one's the converse. So in the next one here, I could do something similar. I can compare UR using the side that's opposite it to RT. Using the side that's opposite it. Well, I could say that it looks like angle Q is less than angle S. So it looks like the segment that's opposite angle Q, which is RT, is going to be less than the side that's opposite angle S, which is UR. Because of the hinge theorem, because angle Q is less than angle S. Notice how this is really, really similar to what we did last section, too. The other half of what this section is about is something called an indirect proof. And an indirect proof, believe it or not, is one of my favorite types of proofs because it's the most passive-aggressive. In the sense that it's like, alright, fine. And it's called a proof by contradiction because it goes, so pretend you're arguing with someone, right? And they're trying to make their point, you're trying to make your point. You go, alright, fine, dude. Suppose I assume that you're correct. If you assume that the other person's conclusion is correct, then what you could do is, essentially, if they are incorrect, then you assuming their assumption is going to lead to some kind of contradiction down the road. It's either going to contradict something that's given or some mathematical calculation or something that we know is true. So what we're going to do for an indirect proof is we're going to temporarily assume our conclusions opposite. We're going to show how this assumption leads to a contradiction. Therefore, if our facts contradict themselves, then it means that the thing that we assume to be true actually isn't. So, alright, this is best done with an example. Suppose I want to prove that there is no smallest positive number. And try to wrap your head around that for a second, because it's actually true. There is no smallest positive number. But assume that there is. Assume there is a smallest positive number. I'm getting lazy here, sorry. Not lazy, but you know, it's hard to write all this stuff on here and not have it be super sloppy. So assume there is the smallest positive number. That's a plus sign for positive. That's step one here, and we could even do these in bullets for all I care. Let's call it x. I'll call the smallest positive number x. Well, what could possibly be smaller than x then? What if I say x divided by 2? Sure, x divided by 2 is still positive, and it's still smaller than x, or it's less than x. So we could say this is a contradiction. This contradicts, that's not how you spell contradicts, whoops. This contradicts our assumption. I'm writing contradicts as, ha ha ha, that stands for contradicts our assumption. Thus, there is indeed, since the thing that we assumed, which is that there is the smallest positive number, led to some false conclusion, we know that that assumption was incorrect. Therefore, there is no smallest positive number. All right, number 2. A triangle cannot have more than one interior right angle. So let's do this according to, if we're going to use an indirect proof or a contradiction proof. Let me pick a different color for this so we don't get the problems confused. We're going to assume the opposite of this. What's the opposite of a triangle not having more than one? Well, there can be more than one then, according to an indirect proof. If we assume the opposite, there can be more than one interior right angle. So again, take a second to recognize why this actually can't be true. Let's give it a point, or let's give it a name. Let's say, suppose I have this triangle down here, totally not at all drawn to scale, and let's say measure of angle 1 and measure of angle 2 are both 90. This is consistent with our assumption. So then, if I look at the, what's that guy called? The duh theorem. The triangle sum theorem. The thing that says all the measures are going to add up to 180. Well, according to this then, measure of 1 plus measure of 2 plus measure of 3 equals 180. We know this is true. We haven't hit any contradictions yet. But if I keep going, if I substitute some stuff in, if I substitute the previous line into this, I get 90. Oh, that was a bad 9. Apologies. 90 plus measure of angle 3 equals 180, which gives me that the measure of angle 3 equals 0. This is impossible. So let's work our way back up because I'm running out of room. Contradiction. Therefore, we can assume that a triangle cannot have more than one interior angle, because when we made that assumption, it led to some fallacies that we know are not true. So notice that, hang on, let me point some things out here. Proofs by contradiction are best done when we're trying to prove the negation of some statement. A triangle cannot have more than one interior angle. There is no smallest positive number. So in doing so, and I guess I'll just be forthright with this right now. There's only one example of an indirect proof on the test that's coming up. And I'm going to tell you to use an indirect proof too. And it's best done when we are trying to prove the negation of something. So we're trying to prove that something is not the case. Like here, look, we're trying to prove that k is not parallel to n. So what we're going to do in this case, where I'm telling you to use an indirect proof, is we're going to assume the opposite and add it to our list of givens. So assume this. Assume k is parallel to n. If k is parallel to n, then this should lead to some weird conclusions that are going to contradict something else we know to be true. So if we say that k is parallel to n, well, let's see here. We know that because of the consecutive interior angle theorem, if k and n are parallel, which we're assuming that they are, then 2 and 5 should be supplementary. So we could say the measure of 2 would be the supplement of 70, which is 110 degrees. We know, or we think we know this, because we assume that k is parallel to n, so this is because of the consecutive interior angle theorem. However, whoa, we should see a problem right here, because we also know that angle, angle 2 is congruent to angle 4 always, because they are vertical angles, because of the vertical angle theorem. Are 2 and 4 congruent? No, which means we've hit a contradiction. So let's state as much. Contradiction. Sure, this contradicts what we know to be true, or contradicts another given that we have, which is that the measure of angle 4 is 100, which means that the assumption that we made is incorrect. So let's wrap this up with a tidy therefore. I know I neglected this last step on the last page because we ran out of room, but therefore we have to get rid of our initial assumption and say therefore k is not parallel to n. Well, that's essentially it. I just figured I'd give us some more practice. So here's one more hinge theorem proof, or its converse, whatever. Not even a proof, just a hinge theorem problem, and an indirect proof on the right. So again, take a pause break, give these a go on your own, and then get started again when you're ready to go. I'm ready to go. So I acknowledge 12 and 12 are congruent. I acknowledge that this unnamed segment is congruent to itself. I did a bad job of showing it, though. There we go. And if I want to compare, if I want to express possible values of x with an inequality, I'm probably going to use the hinge theorem here. Number one, because it's the hinge theorem section, and number two, because this is the only way I have to do that, to get x involved in some kind of inequality here. So what I could say is, because 13 is less than 15, then the angle opposite 13, the 2x plus 5, is going to be less than the angle opposite 15, or in other words, the 66. So remember, this only works if we have these things, the hinge theorem ingredients, which are the two s's in SAS, essentially. So I could solve this rather easily. 2x is less than 61. Ooh, this is ugly. 2x is less than 61, which means x is less than 61 over 2. Which, why not write that as a mixed number? That's 30.5. That's fine. For the indirect proof on the right, we're going to assume, we're given that triangle pug is not isosceles. Get it now, pug? You get this cute little guy on the right. If we're going to assume that pug is not isosceles, or if we're given that information, if we're going to use an indirect proof, we're also going to assume the opposite of the thing we're trying to prove, which again is a negation of a statement, because it involves not, or no, or something like that. That would tell you it's a negation. So we're going to assume the opposite of this. We're going to assume that triangle pug is equilateral. Sorry, equiangular. So okay, under the things that we know about this triangle, allegedly, according to our assumptions and given, is that it is not isosceles, and it is equiangular. Okay, so from there, we could say, what we know about equiangular is that all the angles add up to, all the angles are 60 degrees in a triangle. But we also know, according to some corollary to some whatever, that equiangular in a triangle also implies equilateral. So let's do this. Pug is equilateral. And again, that's according to some corollary, whatever. We can just state it. We don't need to cite that one. So okay, pug is equilateral. We also know pug is not isosceles, but let's remember what it means to be equilateral and be isosceles. So this means PU is congruent to UG is congruent to GP, and that's based on the definition of equilateral. Let's think about what it means to be isosceles. Isosceles means you have at least two congruent sides, which we do. 3 congruent sides is at least 2 congruent sides, so this contradicts the definition. This contradicts the definition of isosceles. So, we have an impossible triangle. We have some impossible facts about the triangle. So what we should conclude then is that we made an error with one of our assumptions. So we only had 2 facts to work with. One was a given, one was the assumption. So that means that our assumption that triangle pug is not equiangular is wrong. Therefore, let's move. Therefore, this is the worst of the handwritings I've had. I apologize, but hey, we're almost done with this video. Therefore, triangle pug is not equiangular. Woo. So, folks, we only have a little bit more in this chapter. This video is running long, so I'm not going to babble here. Thanks for watching, and hey, I'll see you guys soon.